Okay, so here we go. We have a solid disc insulator, charge Q, radius R. It's perpendicular to the page. The disc is in the YZ plane, and a point at its center, projected perpendicularly out, like a normal line, is in the x-axis. And we're going to be trying to find the strength of the electric field at a point that's a distance d from the center. So from the center to here, that distance right there is a distance d. So for my little lead-in before, guess how we're going to slice and dice that up? Guess what we're going to slice it up into?
Shells.
Little tiny shells, little tiny rings. So basically, I'm going to slice it into a little...
What is going on? What is that beach with all the shells, man? That's pretty clever. Ooh. I'm internal.
Now, last time we called the distance from the charge to here, we called that our lowercase r, okay? But this time, and this here was a constant, and we called that the radius of the ring, capital R. But this time, since this green little piece right there, that is our little dq. That is our little piece of all the charge. We're going to be summing up all of the little DEs from each of those rings. And to get them all, we're going to have to integrate over all the R's. So this time we're going to have to label from the center of the disk to right there. That's going to be our lowercase r. That's going to be our lowercase r. And in order to get all the DQs, ultimately in the end, we're going to be integrating over little pieces of dr. And what are we going to have to go from? 0 to big capital R. So we're gonna be adding up ring by ring by ring. So this little piece right in here, this little thing right there, that little piece right in there, that right in there is a little dr. And ultimately, that's our goal, to get to dr. Okay, well, the good news is we already know what the total electric field strength is due to that ring. That was our last problem. So if we look at the electric field strength due to the ring dq, its contribution is going to be dE equals the thing. This disc is in the YZ plane, yes? Just for giggles, I'm going to turn this disc so that it's facing us like this, okay? So I'm going to take that same disc there, and I'm just going to turn it like this now. Oops, whoop, whoop, whoop. Whoa, wrong button. That's the same disc right there, yes? There's the center point. And what we're doing, folks, we're breaking it up into rings like this. And what is this distance from here to here? That's the radius. And what is the distance from here to there? Right in there, this little guy right there. You know, maybe I can make it bigger. Hello. That's just crazy talk now. This little piece right from there to there. Right from there to there. That little increment right there, that's a dr. That's a dr. And of course, from here all the way to the outside right there, what is that? That's the radius of the whole disc. But we're slicing it up into these little rings, and this ring right here, with these positive charges right here, all the charges of this infinitely little thin ring, all of the charge in that ring, that is our dq. And just give me 1 second, and then we'll pause here for a sec. Whoop, not that much. We know what the electric field is at this point due to this particular ring. We just solved for that in the last problem. What is that electric field strength due to just that ring? Anyone? Thank you, thank you, thank you. 1 over 4 pi epsilon 0. Keep going. D. D squared plus r squared. But this time we have to call it lowercase r, yes? Because it's to our ring now. R squared to the 3/2 times, but now it's not the q of the whole ring. What are we calling q of the whole ring? dq. So this is the answer from the last problem. So we'll pause there. Continue when we come back. All right. So now that we know each one of those rings contributes this much, we have to add up all the contributions from all the rings, yes? And right here we have a dq we're dealing with, but we know ultimately we want to add up all these rings by doing it by drs. And we want to do dr from 0 to capital R. So how do we go from this dq to that dr? Well, let's take a look at this, people. Another view, just like we did before, of the disk. Now imagine if I take that little ring right there and I cut it right here, yes? I cut it. and then I roll it out. If I cut it and I roll it out, what will I end up having? So that there is the ring. It's just cut and rolled out. So that's the same ring. Okay. What is this little dimension? Oh yeah, so by the way, that thing there is our DQ. The charge in that is our DQ. So what is this little dimension right here? That's DR. And what about like from here to there? What's that dimension? That's the circumference, which is 2 pi little baby r. And if we multiply those two together, the little thickness times the length of that sliver, what kind of quantity are we going to have? Area. So when we multiply those two together, we're going to get a little piece of the whole area. And guess what we're going to call that little area? dA. So we know that that little area, okay, is going to be dA, and it's going to be equal to 2 pi r times dr. So we can go back over here now. And we could say, look, the total electric field strength is going to be the sum of all these dEs. Which is the sum of 1 over 4 pi epsilon 0 times d over d squared plus r squared raised to the 3/2 dq. And if I was going to do that integral, what would be my boundary conditions? Say it again. 0 to the whole cube. Bravo. But now I'm going to replace that dq, and I'm saying, I'm not going to integrate over dq. Because like this little baby r, this is not a constant anymore. It's going to be different. This little guy right there, that's not going to be constant anymore because it's going to be different for each dq. So I can't just pull them all out and say, oh, they're all constants like before. Each dq is going to have a little tiny different r. So I'm going to have to really deal with that. It's going to be a variable r. So I'm going to replace that dq with this right here, ladies and gentlemen. Ba-bam! Okay, little dA. However, guess what we're going to have to bring into this? Not linear charge density. Which one corresponds with area? Surface area charge density? Does anyone remember the symbol? Sigma. So we're going to have to use the fact that sigma is equal to the charge per area. It's like the surface area charge density. And if I rearrange that and solve that for Q, I get Q equals sigma times the area. So if I have a little piece of the charge, dq, what is that going to be equal to? Sigma dA. But I know what dA is. 2 pi r dr. So that's how I'm going to substitute in from my dq to my dA to my dr. So let's just put it all together now. So this here is going to be the integral of 1 over 4 pi epsilon 0 times d all over d squared plus r squared raised to the 3/2 times dq. But instead of saying dq, I'm going to say sigma dA. But instead of saying sigma dA, I'm going to say sigma times, what's going to go in for dA? Sigma dA 2 pi r dr. And now, to get all the charge, what am I going to have to integrate from? 0 to r. So ladies and gentlemen, the physics is done. It's calculus time. Now it's just time to do that integral. Whoops. All right. So I'm going to pull all the constants out. I'm going to pull all the constants out. And what are we going to have here? Pi, sigma. What constants do we have up front? Andy, come sit up here. Or leave. But don't sit there and talk. You get on my nerves. Okay. What constants am I going to have out front here? So 2 epsilon 0. So sigma over 2 epsilon 0. Is that it? Oh, there's a d there too, yeah. Yep. And then this is going to be the interval of 0 to r of r over d squared plus r squared raised to the 3/2 dr. integrate that. Um, I use a U substitution, and I know every time I say that, everyone says, "No, it's like a chain rule or something." All right. So you do it your way. I'm gonna do it my way, and then let's just compare answers here. Okay. So I'm gonna let U equal d squared plus r squared. So du dr. If I take the derivative of u, that's gonna equal 2r. So du is going to equal 2r dr. So 1/2 du equals r dr. So then this is going to be sigma d over 2 epsilon 0 integral u 1 over u to the 3/2. R dr, which is 1/2 du. So I made this u substitution. This is going to be the integral sigma d over 2 epsilon 0 the integral of u negative 3/2. It's going to be 4. 4, bring that one out. Du is going to equal sigma d over 4 epsilon 0 times u to the negative 1/2 times 2. Now, instead of like figuring out my new boundary conditions in terms of u, before I have to substitute in these numbers, I'm just going to transform it back to my r business, and then I'll substitute in numbers. And did I do that integration correctly? I believe it's so, yes? Negative 2u to the negative 1/2. So then this is going to be sigma d 4 epsilon 0 times negative 2 times d squared plus r squared to the negative 1/2. And now, my boundary conditions, since I put it back in terms of r, I can bring back 0 to r. So now I plug in R and I plug in 0 and I have to subtract the 2. Yeah, don't forget to plug in 0, because that's I don't know if you remember, that's a mistake we made one time after school. We forgot to plug in 0. So you got to go back and plug in 0, and that's a very crucial term right there. It doesn't just cancel out. It's going to be 2 over D minus 2 over square root of. And so if you get a common denominator, what is that going to be? 2 square root of D squared plus R squared minus 2D all over D times the square root of D squared plus R squared. I don't know, is that worth even doing that? Probably not. Yeah, I guess that's not even worth doing that. Did you get the same answer as me? I'm going to pull out the 2, so I'm going to have sigma D over 2 epsilon 0 times. You know what? I am going to combine those suckers. If I combine those suckers, let me see, what do I do here? Oh,
I don't think we should combine it.
you know what I'm gonna do? I'm gonna distribute the D. That's the only thing I did. I'm gonna distribute that D right here. If you distribute the D, then I already took the 2 out there, so I already did that with the 2. I took the 2 out, and then if I distribute that D, what am I gonna have the first term right here? If I distribute the D, pull the 2 out and distribute the D. Anyone? 1. 1 minus D over the square root of D squared plus R squared.
You take out the D from the other fraction.
What's that?
You take out the D from the other fraction. The one right next to it. Yeah, like it says sigma D. Over 2 plus yeah.
Oh, yes, yes, yes. Thank you, thank you, thank you, thank you, thank you. Chad, you're the man. Took that D out. Thank you, thank you, thank you. That's the D I distributed. Andy, thank you. See, I think you should sit there all the time now. You're helping me out. All right? All right, that's it, people. We found the strength of that electric field. Oh, wait a minute. Should we replace sigma? If we wanted to replace sigma there, what would we substitute in for sigma? Q over pi r squared. So if we did that, help me out.
Didn't we take that before?
Q over pi r squared over 2 epsilon 0 1 minus d all over square root of d squared plus r squared. Yeah. Where did that come from? The square root of d squared plus